When you want to do some chemical reaction, unless you're working with a particle accelerator, you probably aren't going to use one atom at a time. Take Amedeo Avogadro's advice and just use an enormous amount of atoms. It's easier to measure anyway. When you use chemicals, you probably mass them on a scale and measure their volume. But just because you might mix two chemicals of equal mass doesn't mean they're the same number of atoms in each chemical. Take a look at the periodic table. The atomic masses of the elements aren't all the same. In fact, they're all different. Remember, they have different numbers of protons and neutrons, so some are heavier than others. This presents a problem when we need to deal with ratios to get a good yield from a chemical reaction. Here's what I mean. Imagine you have 10 pounds of tea kettles and 10 pounds of rubber duckies. Will you have the same number of kettles as duckies? Unless you have huge ducks or tiny kettles, odds are there will be lots more duckies. But if for some reason I needed the same amount of kettles and ducks, I could just say I need a dozen of each. I know that a dozen is 12. Now, since atoms are so freaking small, we need to have a massive number to even see them with our eyes. So, just like a dozen means 12, a mole means 6.02 times 10 to the 23rd power. It's just a word that represents a large number, which is also called Avogadro's number. No, not avocado, Avogadro. In a balanced equation, you can compare the amounts of reactants and products using moles for the amounts. 4 moles of iron react with 3 moles of oxygen to produce 2 moles of iron 3 oxide. But we're getting ahead of ourselves. Let's go through the basics for balancing equations. I like explosions, so let's start with a reaction. Acetylene gas combusts with oxygen to create water and carbon dioxide. Also, it's awesome. Start by writing the skeleton equation, or unbalanced equation from the sentence. Acetylene gas has the formula C2H2. Words like combust, react, explode, and so on mean you need to use the arrow. With means the plus sign. Oxygen is a Brinkelhoff twin and needs to be diatomic. Then it creates water, which is H2O, and carbon dioxide. This is the basic equation. But right now, it's not chemically true. Here's why. Here is acetylene, and here is oxygen. If we slam them together and add some heat, nothing will happen if there's just one of each. The ratios, or stoichiometry, isn't right. I can't make water and CO2 without creating and destroying matter, and that's a big no-no according to the law of conservation of matter. So, we actually need 2 molecules of acetylene for every 5 molecules of oxygen. When they react, they rearrange and make 2 molecules of water and 4 molecules of carbon dioxide. Now the equation is balanced and true. Let's try balancing equations without drawing out the atoms. Aluminum reacts with oxygen to produce solid aluminum oxide. Let's write the skeleton equation and write the descriptors where appropriate. Aluminum is a metal, and it's solid. If you didn't know that, you're overthinking chemistry. Aluminum foil? Yeah, now you remember. Oxygen is a Brinkelhoff twin and a gas. And aluminum has a +3 charge when it forms an ion, so solid aluminum oxide must be Al2O3 to be neutral. I like to draw lines to keep my balanced process clean and organized, but it's not necessary. These next steps are what I find easiest, but you could do this in your head if you're able. This way is a good check for your process, though. Write the elements present in the reaction on both the reactant and product side. Write the number that exists on each side. It looks as though aluminum is being created, and the same for oxygen, so we're going to need some coefficients on the reactant side for sure. Let's fix aluminum first. I put a 2 in front, and that fixes the aluminum problem. Now oxygen. There's no way for me to turn a diatomic molecule into an odd number, so I'm going to need to put a coefficient in front of the aluminum oxide to create an even number to work with. Start with a 2, and adjust your numbers. Now the aluminum is 4, and the oxygen is 6. Now we can go back and fix the reactant side. Turn the aluminum coefficient into a 4, and give oxygen a coefficient of 3, bringing the total to 6. Now both sides match, and we've obeyed the law of conservation of mass. Let's do another one. Ammonium phosphate and lead-4 nitrate react to create lead-4 phosphate and ammonium nitrate. This one's trickier. You may need to look at a list of polyatomic ions to do this one if you don't have them memorized. Here are the neutral formulas in a skeleton equation. Let's get ready to balance. When you see polyatomic ions together, sometimes they don't change during the reaction, and that's the case here. So to save time and energy, keep the polyatomic ions together when you balance the equation. Ammonium, phosphate, lead, and nitrate on both sides. Write down the current numbers. A good place to start when balancing equations is to balance any metals first. So let's fix lead. Put a 3 on the reactant side and change the numbers. This means nitrate is actually going to be a 12 because 3 times 4 is 12. I can see that a 4 in front of ammonium phosphate would kill 2 birds with 1 stone, so I'll do that next. 3 times 4 is 12, and phosphate gets a 4. Let's fix the product side. If I put a 12 in front of ammonium nitrate, I'll be done. Now the equation's balanced. Happy studying!